To finish out our chapter on partial differentiation, I'd like to introduce the subject of Lagrange multipliers. Not to be confused with the hit song by ZZ Top called Lagrange. It's the one that goes, ah-how, how, how, how. I'm sure you've heard it, and if you haven't heard it, ask your parents about it. Lagrange multipliers deals with the subject of what's called constrained optimization. That is to say, we are going to either maximize or minimize a function of multiple variables with restrictions on the independent variables. So to give you an idea of what something like this might look like, I would like to maximize and minimize. We'll say f of xy is equal to x squared plus y squared. Oh, let's make it even better. Let's do the square root of x squared plus y squared, subject to, let's do x squared plus 4y squared is equal to 4. Now, typically what you have here is the function that you're going to optimize is referred to as the objective function. This function down here that's being set equal to a constant is referred to as your constraint function. Is your constraint function. The constraint comes from the word used up here, constrained optimization, so your constraint function. Now, what I'm going to do is give you a graphical idea of what's going on and then extend that so that instead of talking about things graphically, we can talk about them in a more algebraic format. Now, for those who don't recognize it immediately, f of xy is equal to the square root of x squared plus y squared is actually the top half of a cone. Grab another color here. So mindset to get into for this one is that this would be like saying this is the top half of z squared is equal to x squared plus y squared. So level curves of this thing would be circles. What I'd like to do is draw several level curves of f so that you can just sort of see what's going on. So if we were to set it equal to 0, we would get just a point at the origin. And if I set it equal to anything else, then it's just going to be a circle of radius, whatever I'm setting it equal to, centered at the origin. So we could see a circle of radius 1. This is k equals 1. We could see a circle of radius 2. K equals 2. We could see a circle of radius 3. And so forth and so on. Basically, if it looks like a big symbol for target, you're doing it right. Now, the idea is I am only allowed to be on this curve, though. X squared plus 4y squared is equal to 4. Though it's not in standard form, you might recognize this one. This one is a conic section. And in standard form, this would be x squared over 4 plus y squared is equal to 1. So real quick, I do note that if I were to draw this, it is centered at the origin. If I were to set y equal to 0 and solve for x, I would get x is equal to plus or minus 2. So we'll point out those two. And if I were to set x equal to 0 to get my y-intercepts, I would get y is equal to plus or minus 1. And so the ellipse overall looks kind of like this. And if I draw it just right, it actually looks kind of cool. Of course, now that I've said that, I'm going to jinx myself. But yeah, it looks kind of like an eyeball staring into your soul. So the idea is, I can only be on the red curve here. The question is, what is the largest k value that I hit, and what is the smallest k value that I hit? Well, the points in question, we'll switch back to green, would be you are minimized right here and right here at a value of 1. You are maximized right here and right here at a value of 2. So the minimum value of the function is 1. and the maximum value of the function is 2. Every other point that's on the ellipse, like all of these points in the middle, are somewhere between 1 and 2. If I wanted to draw more concentric circles and figure out points of intersection, I could, but since we're just going for optimized values, those are the only 2 that I need. Now, here comes the interpretive part of what we're doing. If I were to consider tangent lines at all of these points of intersection between the level curves and the constraint function, those tangent lines would all be parallel to each other. Just as important, the normal vectors would all be parallel to each other as well. The normal vectors are supposed to be orthogonal to the level curves. Now, those normal vectors that we're seeing here would technically be gradient vectors. Those would be paths of steepest ascent or steepest descent, as the case may be. So, important concept. The gradient, we'll say gradients, of f and g are parallel at these points. So here comes the big important conclusion that we draw regarding Lagrange multipliers and constrained optimization. You are going to be setting up a system of equations that states the following. The gradient of f is parallel to the gradient of g. Now by parallel to, I mean it's going to be a constant multiple times the gradient of g. The constant multiple that they've decided to use is the Greek letter lambda. Now this is merely speculation, but when it comes to naming mechanisms in math, usually the easiest explanation is the most correct. These things are called Lagrange multipliers. Lagrange starts with L. What's L in Greek? Lambda. So there you go. Now, if you take this, what you're actually going to be doing is creating a system of equations. So when you're setting these equal to each other, what you're really saying is that the partial derivative of f with respect to x is equal to lambda times the partial derivative of g with respect to x. Partials with respect to y will be equal to each other, and so forth and so on, depending on how many variables you have in place. Then you'll also have one more equation, which is your constraint equation. So if f is a function of n variables, what you'll be doing is setting up a system of n plus 1 equations with n plus 1 variables. To demonstrate this, we'll do that in the next video. I think this one's probably long enough.